Alrighty. So you want to look at number 3. And number 3 says that we have a state psi of x comma y comma z equals c xy plus yz plus zx e to the minus alpha r squared. So far, so good? And then the instructions say, rewrite this wave function in terms of the spherical harmonics. From that, determine the probability of a measurement for total angular momentum, finding it to be in state L for all possible values of L. Likewise, determine the probability of a measurement of angular momentum in the z direction, returning a value of m for all possible m values. The following definitions for x, y, and z in terms of spherical coordinates will be necessary. X equals blah, y equals blah, and z equals blah. And so it's changing from x, y, z into spherical coordinates, and then we're going to go from spherical coordinates into spherical harmonics. Now, I have to point out a couple things. We haven't learned what the operators for angular momentum and z coordinate of angular momentum are. And so you have to understand, right, we just haven't gotten there in the lecture yet. Well, in theory, we would today, but we're going to get there tomorrow. Even without this lecture or this going over the homework, we'd still get there tomorrow. So what I will tell you simply is that L tells you the total angular momentum, and I'll write it down here just. So L times L plus 1 times h bar squared is the total angular momentum squared. And then the component of the angular momentum in the z direction is m h bar. And so m is specifically telling you what the component in the z direction is of the angular momentum, and L is telling you what the total angular momentum is. And one of the interesting outcomes that I'm just going to say now, because I have it all written out, is that you can never have L sub z equal L. Because L is square root of L times L plus 1 h bar. Which is bigger than L h bar, right? Because L times L plus 1 is bigger than L squared. And so the z component, m can go all the way up to L or down to minus L, but it can never reach higher than L. Hence, you can never have your angular momentum all in the z direction, which seems really weird. That's like saying you can never travel perfectly north. You can head in a northerly direction, but you can never go perfectly north. It's not possible, is basically what this is saying. And yes, it's just a weird outcome of quantum mechanics. Okay, so this is to make sense of what we're doing in terms of the final answers. The rest of it, totally what we can do.
And also, so why is m the component in the z direction?
We'll get to that.
Okay.
That's not a simple one-word answer. And I do hearken back to, we'll call it M when we were separating variables, you know. We'll call this, I don't know, L times L plus 1. I don't know, you know. It seems really stupid when we were doing it, but it's because it makes the answers come out nicely in the end. Okay, so now, doing our work, I'm going to take this and say, well, if X is this thing and y is this thing, I'm going to have okay, so the stuff in the middle I have to put in, I'm going to put it in tiers. You know, XY would be my top tier, YZ the middle tier, and ZX the bottom tier. Because there's no other way to make it fit, really. So doing the xz first. So x and z both have an r out front, so we're going to have r squared. And then the x has a cosine theta, or has sine phi, sine, or excuse me, just going to the right, sine theta. Z has cosine theta. So I'm going to have sine theta, cosine theta. And then I have to multiply, well, no, I don't have to multiply. Then I just have e to the I phi minus e to the minus I phi all over 2I. So that's xz.
Why do you have to put in the exponentials? Because weren't there two relationships?
There were two. And the reason I did, it's a very good question. I just went there. I actually thought about it when I was writing it, but I didn't say it. If we look at our spherical harmonics, our phi relationships are all e to the I m phi. And so having it like this is m equals 1, this is m equals minus 1. And so that's why I put it in that form. Whereas we have the trig functions for the theta portion. So I'm leaving that in sine and cosine of theta. So it's a really good question. Why did I do that? Because that's how I'm going to pick off the terms. I'm going to, after I'm done, take all the terms that have e to the I phi and put them together. All the terms with e, and so on. Okay, so there's my first one. That's xy. Now yz. So yz is going to again have r squared. And then we have sine theta, cosine theta again. But now we have e to the I phi plus e to the minus I phi over 2. And finally, doing zx. Hey, we didn't have any x. Oh, I did xy wrong. I did xz. I did xz first. I was thinking that was the hard one. XY is the hard one because we have to multiply, although it's not really hard. So if we do the XY, we're going to have r squared, and then we have sine squared theta. And then I'm going to have to multiply something with e to the a minus e to the minus a times e to the a plus e to the minus a, which means my cross terms, well, maybe I should write this out. So I'm going to write this down here. So there is just brute force, not thinking at all. Just doing like you learn to do whenever you learn to multiply. But then being smarter people today, e to the I phi times e to the I phi, you add the exponents. So the first term is e to the 2I phi. The second term, I phi minus I phi, well, that's e to the 0, right? And then I have a plus and a minus. So it's plus 1, minus 1 for the two middle terms. And then the final term minus e to the minus 2I phi. And so there's the multiplication that I need to finish out up above. So I'm just going to take this, duplicate this, shrink it a bit, and put it there. It still doesn't quite fit with my work down below. But now, this is, I don't know, I consider it wonderful. I'm now ready to go. So first of all, I say I have e to the, breaking it down by my exponents. So rewriting psi again, but breaking it down by my exponents. All of them had that, so I'm leaving that out front. And now I'm breaking down by the exponents, so I'm going to have e to the 2I phi. Well, e to the 2I phi was multiplied by sine squared theta over 4I. Right, this is the sine squared theta, there's the 4I. Plus e to the I phi. And if I look at e to the I phi, it occurred two places. E to the I phi occurred there and there. Both of them were multiplied by sine theta, cosine theta. One was divided by 2, one was divided by 2i. So what I'm going to have is, change back to a writing pen, sine theta, cosine theta over 2. And then taking the one that did not have an I, that's a 1. 1 over I plus 1 over I is the same as minus I. So that minus I is the same as the plus 1 over I. Then I'm going to have e to the 0. E to the 0. Actually, I have does not occur here. Look at my answers. Yeah, it does not occur. That's right. It does not occur. These. Right. My last plus e to the minus I phi. E to the minus I phi again has the sine theta cosine theta over 2. And then I'm going to have a plus sign and then minus 1 over I, which means 1 plus I. And finally, e to the minus 2I phi is multiplied by the same sine squared theta over 4I. That is the same as what we had for the plus 2I. So now I have them separated out by the e to the I phi terms. Now we have to look at our spherical harmonic list. So do you have a list of spherical harmonics available to you? If not, what do all of these have in common? Well, I see that I have a typo in my answer. I'll fix that before I post it, because that would be embarrassing. So these things that have, well, let me just fold this over and bring it up again. Here's the spherical harmonics for L equals 2. And so you have e to the 2I phi, e to the 1I phi, e to the minus I phi, e to the minus 2I phi. We don't have any without this, so we can rule that out. Notice each one has the sinusoid is squared out. If we look at the others, I didn't bring, I'm just going to run to my, I will go to the presentation from last class period. I can throw that on the screen. Quantum 28, hydrogen atom. Nope, that's today. 27, that's the one. Okay, I had the, there's a quicker way. I had the spherical harmonics here. So here we have the spherical harmonics, and you can see, I left my stylus over there. You can see that for the L equals 1 variations, well, these are in terms of YZ. I just didn't stop to think. I could have done it this way because I have them here in terms of XY and YZ and XZ. Except for that's what you did, and you don't get this term here when you do that. I am a little confused as to how that works out differently, but going with it anyway. Here's the L equals 2 variations. And so you have the sinusoids are the second power, this one here being second power, and then 1 for the L equals 2, whereas the sinusoids refer to the first power for theta for the L equals 1. And so I'm working with the L equals 2, and taking, I am a little concerned, why is it that this one here would not show up if I did it by the XY, whereas it does if I do it this way. But I'm going to keep going and try to figure out why there's that inconsistency later. So if I look at these, the one with sine squared theta is -2. The one, or actually -2 or +2. And so I have to look a little more carefully. What is cosine squared phi minus sine squared phi, and what is cosine phi sine phi? So if you do that, notice it's the 2i on bottom squared gives you a -4 on bottom. Now this color is actually easier for you to read than me to read. I'm changing colors because I have a hard time with this one. Oops, that's still 2. Okay, I think I see a difference now in what I have written. And so you should have that, which is exactly in agreement with what they have. Let me go grab the textbook just to make sure that I have these spherical harmonics, because the textbook, I'm pretty sure, has them. Well, I mean, I know that if it's m equals -2, it's e to the minus 2.
I was just writing that.
Right. cosine become either like, okay, this is really precise.
How there's a difference between interpretations here of the spherical harmonics has me confused, for sure.
Me too.
So, in the textbook, these are the spherical harmonics I'm working with right here.
Mm-hmm.
And so 2 plus or minus 2 is all the same stuff with e to the plus or minus 2iv.
Okay.
And that's the way that we derive our spherical harmonics, right? We got our solutions, e to the imv was the m part. And so if it's m equals minus 2, it has to have minus 2 up there. If it's m equals minus 1, it has to have minus 1 up there, which is, I didn't even notice that, yeah, it's going to have, with that listing, something different.
Oh, okay.
And so, honestly, I know I got this from somewhere. It should make some sense, but it doesn't make sense, at least by the way I've always been taught to derive the spherical harmonics.
Okay.
So that means this was a bad choice of spherical harmonics to look at. The ones that I showed you, of course, were the ones that are in agreement with what we have in the textbook here. So going back to, of course, the wrong one. This one then, yes. So now I'm going to have this here is going to have to be something with, because it has sine, cosine, it's second order in that. This is going to have to be something that's L equals 2, M equals minus 1. This one here, L equals 2, M equals minus 2. And then the ones above, L equals 2, M equals 1, and L equals 2, M equals 2. So we have those 4 values of L accounted for. But I need to figure out what the proportions are for each of these. So to figure out the proportions of these, I'm going to use e to the 2I phi sine squared of theta times square root of 15 over 32 pi equals y22. Therefore, e to the 2I phi sine squared theta is equal to y22 over So I'm going to make that substitution. And likewise for the rest of them using, I know you don't have this in front of you, but using the this list of spherical harmonics. So what I get is, and now I'm copying from my solution rather than having to carefully reason each one out and do the math. My body apparently is not happy. Now, something I just wrote I wrote this out, and this is the way you should get it when you do your work. If you follow the textbook's spherical harmonics, this is the way you should get it. But please note that 2 times square root of 8 pi over 15 is exactly the same as 32 square root of 32 pi over 15.
Why did they write it?
I wrote it differently because you have square root of 15 over 8 pi for the m equals plus or minus 1 constants.
Okay.
So this is using the constant as given in the spherical harmonic. But then we have that 2 because these were only over 2 instead of over 4. So that's why there's the 2 out front, which then brings them to be the same.
So you're multiplying by what you divided by?
Well, so what I'm doing to get this right here is I took the 4s. So let me erase those 2 circles. This had over 4. This had over 4 here. And this had over 4 here. This had over 2. So I factored out of over 4 and put a 2 there. Likewise, this had over 2. So I factored out of 4 and put a 2 there. And so I have this stuff that was already out front. And then I brought out an over 4. And that's what brought in these 2 2s.
Okay. And where are the i's coming from?
The i's are right there and right there.
So why do you have 2 times 1 minus I?
Oh, well, there's 1 minus I there and 1 plus I there.
Why do you have them both 1 minus I then?
Because I miswrote on the second one. I didn't notice that I had written that wrong. The second one is a plus. Right, the one with the minus is a plus sign there. So the neatest it can be is c square root of 2 pi over 15. Where's that 2 pi come from? That 2 pi comes from dividing out. I had this 4 out front. And of course, inside the square root, 4 becomes 16. And so 32 divided by 16 leaves me 2. So that's where the 2 pi comes from. And then I just didn't give myself room, times r squared e to the minus alpha r squared. Okay, I know my handwriting here is getting really hard to read. But now I have a constant out front and a radial portion that's not part of the spherical harmonic. Right, that radial portion is going to tell us about n. If we'd asked about n, I would use the spherical or the radial portion. But I'm only asked about the spherical harmonic, so now I'm only looking at the part in the brackets here. And so I have those 4 pieces, and there's 2 ways you can go about this now. The easiest way to go about this is to simply recognize, well, the magnitude of 1 minus I, and I have to go to, I'm done with this page. I'll write it out again. This time it'll be readable.
Was there a place we dropped a minus sign earlier? That term is minus 1 minus I?
I was thinking about that. Let me look and see. It's not beyond the realm of possibility that I made a sign error. sign errors do occur with regularity in this kind of work. I noticed it seemed inconsistent as I was writing it. Okay, so there is what we have now in terms of the spherical harmonics. Okay, going back to just check what you said. So we had minus here, 1 plus, plus, plus. Yeah. Oh, I wrote something wrong. There was a minus sign right there. So that changes the sign of that one. That was the issue. That's in the definition for y 1, 2, you have a minus sign that you don't have for the others. So that was where it came from. I'm glad you asked, because when I was writing, I was like, something seems wrong, but okay, so there's two ways of going about this. One way is to go ahead and calculate the magnitudes of everything and do everything perfectly. That is, I know that the probability of y22 is that. Taking just the mod squared of the coefficient of y22 and not worried about the radial part. Except for we have to figure out what c is, right? Well, I could also say, okay, I've got the things in the brackets. And if I add up the probabilities of y22, y21, y2 minus 1, y2 minus 2, it's going to have to come to 1. And so that means that I should just be able to take not just those, but if I take the full of them. So I can just take these and say, what is the magnitude of this mod squared plus this mod squared plus this mod squared plus this mod squared, and then take the mod squared of each one divided by the sum of those, and not worry about the external stuff, right? Because what I'm saying is this stuff is a constant that will be on this here will be in both the numerator and denominator of every term. And so I'm just not going to worry about it. And so I'm going to have, let me say, let's see, what did I call it something? Yeah, I just called it a minus I mod squared plus 1 minus I mod squared plus 1 plus I mod squared plus I mod squared. So I believe that comes to 6. I did these in my head, so I could be making a mistake, but I think that's pretty straightforward, right? 1 minus I mod squared is 1 minus I times 1 plus I, or 1 minus I squared, which is 1 plus 1, 2. And so the probability of m equals minus 2 is equal to I mod squared over A is equal to 1 in 6. And the probability of n equals minus 1 is equal to 1 plus I mod squared over A equals 2 and 6, or if you prefer 1 and 3. And then because of the symmetry for n equals 1 and n equals 2, we're going to have the same things. So we have 1, 6, and 2, 6, and 2, 6, and 1, 6, a total of 1. Now, I skipped over one thing. I just realized Chad wasn't part of the conversation when I talked to Aaron about this. What's the probability of being at L equals 0? Zero because, sorry, I've got some orange in my teeth. Is 0 because we have no spherical harmonics for L equals 0. What's the probability of being L equals 1?
What are all our possible L values?
Okay, L values can be 0, 1, 2, 3, 4, etc. And those are the bottom numbers of the spherical harmonics. So which spherical harmonics are present?
1, 12, 4.
Well, the bottom numbers. What bottom indices do I have on the Y's?
2.
They're all 2, right? So what's the probability of being in L equals 1? 0. Probability of being in L equals 3? Probability of L equals 2? Right. Right, so I skipped over because I talked to Aaron about it on Friday. Since they're all L equals 2, it has to be L equals 2. There's no option. How did I know they're L equals 2? Because I looked at the power of the sine, cosine terms. And then my M's, M if the top number, so we had -2, -1. And so that's why these are, I know that says N, but these were M's. Probably being M equals -2 was just taking the magnitude from the -2 inside the bracket, dividing by the sum of those magnitudes from inside the bracket. That's what gave me the 1/6. All right, so better understanding? What?
Yes, sort of.
Oh,
I think the spherical harmonics that you had on the slides were giving incorrect answers for number 2 as well, if I'm not mistaken.
Yeah.
Like when I looked in the book, I was able to match my answers with the one I got for the Y2 too.
yeah, I had never noticed that those weren't the same.
Yeah.
And it could be that it's using a different coordinate set, is how they get there, right? Because the choice of where your z-axis is with respect to theta and phi makes all the difference. And so if you choose phi going from 0 to pi, you're going to get a different xyz correlation than if you choose phi going from pi over 2 to minus pi over 2. Right? It's still the same thing, but it looks different. And because our calculation was done based on the z-axis being phi equals 0, that's the way I'm doing everything. So yeah, at least now I understand where yours came from. And yeah, it would be much easier with yours because you can just read off X, Y, and you're done.
Well, I still converted them to the sine and cosine. I just didn't do the exponentials.
Yeah. Yeah, and that was your first question. Okay, so we got 10 minutes left. Why not start the lecture? What do you say? Sure. So what I have here is stuff filling in blanks that I left class last period. I skipped over them because of time. Since we only have 10 minutes, it's great to fill in the blanks. So derivatives. Remember I said just a lot of calculus, we're going to trust the book. Well, here's actually showing the derivatives. du, d rho. What was u? Oh, okay, we have to go all the way back. Oh, no, I don't have, I do have it about 3 slides after. Oh, no, okay, there it is. So here's u. We have the solution for large radii here, for small radii here, And then we had this infinite polynomial for the middle ground. And then we have our Schrodinger equation, this very simple looking beast, which requires a second derivative. And so the next page is taking the second derivative of u. And so the first derivative, really ugly, doing it brute force, collecting terms not as ugly. Then taking the second derivative, so taking the derivative of that, really, really ugly. But then collecting terms not as ugly. The beautiful part comes when you put it into this Schrodinger equation, when you set that derivative equal to 1 minus rho 0 over rho plus L times L plus 1 over rho squared, u. Then, and I said that's beautiful. It doesn't look beautiful here. But then collecting terms, it simplifies to a shorter equation, which always makes me happy. But we're not done because we now need to figure out things about v, that function v. So with v defined as this power series, we take the derivatives and we looked at these derivatives. And then if I put those derivatives in, I actually want to rearrange this equation. Notice this has a row here and then no row for these two terms. That's going to give you different powers of rho if I use the same dv rho. Likewise, well, no, that's the only one I have to worry about here. So rearranging a little bit, we put in, and I think we did this in class last week. So there's putting in the derivatives of v appropriate, and so we power of rho. And the only way that this can be true is if it's true independently for every j. That is, since we have rho to the 1 times all this stuff is 0, and rho to the 2 times all this stuff is 0, and so on. All this stuff in parentheses has to be 0, because, of course, rho isn't always going to be 0. And so we take all the stuff that's in parentheses and say that's equal to 0. Well, what we did is we took the terms that had a c subscript j plus 1 and put them on one side of the equation, the terms that had c with the subscript j on the other side of the equation. And so we have c subscript j plus 1 times all of this stuff equals c subscript j times all of this stuff. And then we solve that for c subscript j plus 1 as a function of c subscript j. So this gives us a relationship so we can build up what each of the next levels is going to be for the c sub j's. So if you know what c sub 0 is, then you can calculate what c sub 1 is, c sub 2, and so on. Right? That's the idea here. But then we face reality. In the large radius limit, L plus 1 are insignificant compared to j, so j times L plus 1 is just j. Likewise, j plus 1 is just j. J plus 2L plus 2 is just j. So this whole thing in the large radius limit, that's j. So we have 2j minus rho. Well, rho is insignificant compared to j if j is really large. So the top just becomes 2j. In the bottom, this is j. This is j. So in the bottom, we have j squared. And so if we cancel a j, we have for the large j limit, c sub j plus 1 is c sub j times 2 over j. And you might wonder, why are you doing this? I know when I was reviewing my notes for preparation of today's lecture, I was thinking myself, now why do I want to do this? I want to do it to prove a point. Here's the point. If we say, okay, for large j's, that's what the c sub j looks like. So let's say that our c sub j's are going to approximately always be that. Now, they're not for small j, but we're putting that in. In that case, my v as a function of rho is the sum from j equals 0. And so I'll write this down. But if you do that, it turns out that's equal to C sub 0 e to the 2 rho. No minus sign there. That was a mistake on my part. So what we found here is the solution is going to be an exponential to the 2 rho power. And you might say, great, we found a simplified solution. I mean, that's simpler, right? But if we put that in, remember we had U equals our small radius solution. I said small and then I wrote the wrong one. There's our small radius solution multiplied by our large radius solution multiplied by our intermediate solution. Change color for the intermediate solution. But if you multiply that through, you now have something that's e to the rho. Now we have a problem because what happened to our large radius solution? Yeah, it got destroyed and now it's going to blow up for large radius. This cannot be the right solution because it blows up. And, okay, like here, college students saying this for the first time, the natural response is, it cannot be done. But, you know, like if you take particle physics, you'll see things that cannot be done taken to extreme levels until they find a way that they can do it. And so in this case, what would make it so it doesn't blow up? There's one simple thing. If this goes to some n, instead of going to infinity, then it's not equal to this and it doesn't blow up. If that series truncates and doesn't go to infinity, then our solution is fine. And so the only way our solution can be correct is if it's not an infinite series. So now remember, why did we choose an infinite series?
It's a way of showing the wave function for intermediate rows.
Yes, but we chose that specific function because any function can be written as a superposition of each of the of an infinite polynomial. Any function can be some amount times rho to the 0 plus some amount times rho to the first plus some amount times. You can do any function by doing that. So that's why we chose this function. But now, after using this function, we say, well, it works, except for it has to truncate. So we now can't be any function, but it can be the function we need. So it must truncate. And so that's where we define, okay, if it's going to truncate, now let's go back to our recursion relation. Our recursion relation was that C sub j plus 1 equals C sub j times this stuff in brackets. So if it ends, C sub j plus 1 equals 0 equals C sub j times and I'm going to put a max here. You can't read my max, can you? Just erase everything. So if that's equal to 0, the numerator has to be 0. And so that's going to require 2 times j max plus L plus 1 minus rho 0 equals 0. To simplify our lives, we call this thing right here n. And that's our principal quantum number. This is where the principal quantum number comes from. It's a term that tells us about the truncation of our polynomial. And furthermore, we now have 2n minus rho 0 equals 0, which means that rho 0 must equal 2n, right? But what's rho 0? Now we go all the way back. All the way back. Kappa was defined as this stuff. And rho 0 was defined in terms of kappa. And so rho 0, if you put kappa in, expands to this thing here. Or solving for E is dependent on 1 over rho 0 squared. So now since we had rho 0 is equal to 2n, then this is equal to minus me to the fourth over, and I have 2 squared is 4, 4 times a is 32, pi squared epsilon 0 squared, h bar squared, n squared. So now we have our energy is dependent on the n value. So energy, yeah, it's still the same thing. Having a word for a minute, is dependent on n. So our principal number tells us the energy. And we're out of time.